some of these questions. I think we talked about this is chapter 2. Let's go to chapter 4. Okay. So we talked about belief, policy, state. I'm not sure if we talked about this question. In the discussion of active inference in POMDP, belief updating about policies, we find that the posterior that minimizes the free energy does a posterior at time t. Oh, we did discuss this. Yeah, we did discuss this last time. So this question, I think we did not discuss pi being a policy or a model last time, or did we? I think we didn't get to this.
Yeah, I don't think we discussed that.
All right, so we can open it up and we'll start here, I guess, with the most upvoted. So the question reads, what is pi? On page 69, the authors write, at each time step, the current state is conditionally dependent on the state at the previous time and on the policy pi currently being pursued. Then on page 71, they write, thus we can interpret the priors of equation 4.6 combined with the likelihood of equation 4.5 as expressing a model pi of a behavioral sequence. So which is it, policy or model? And then they suggest a rewrite of the sentence. They say that thus we can interpret the priors of equation 4.6 combined with the likelihood of equation 4.5 and the transition probabilities B sub tau pi as expressing a model for a behavioral sequence where the model is a function of policy pi. And then there's some discourse here. So in this reframing, can we say that the model simulates the agent in the environment as if it had taken the actions in the policy? And I don't know, does anyone have any, I don't know who asked that question. Oh, Eric, that was you? That was your question? And then does anyone want to maybe take a stab at answering that question? Or we can continue reading what was written here. So what's written here says that on page 69, the authors also say policies here may be thought of as indexing alternative trajectories or sequences of actions that could be followed. On page 71, they define the likelihood in equation 4.5 as a matrix A that expresses the probability of an outcome. They describe the priors of equation 4.6 as the prior over the initial state, vector D, and beliefs about how the state at one time transitions to the state at the next time, matrix B. And they also say that the transitions are conditionally dependent on the policy chosen. Because of this conditional dependence, we can see how the policy influences the model and why the authors may use the terms interchangeably. So does anyone have any comments there?
I guess I would say that answer in discourse kind of agrees with what I proposed, which is that strictly speaking, we should treat the pi as policy, but it behaves as a model. But once it's executed, it's implemented, then the model has become a function of the policy we've seen so far. So I'd say that's that's compatible interpretation. So I think strictly speaking, it would be better if the text was consistent and called pi a policy, and then say, yeah, the model is a function of pi. That'd be my interpretation.
Yeah, I definitely agree with that. I think that the model is policy specific. So yeah, but they could do a better job of, I mean, the variables, as we've seen, are so ambiguous anyway, so it could definitely be a lot better.
And by the way, about the topic of consistency, actually, I gave some thoughts about the issue we were discussing in yesterday's math learning session. And I also consulted some other papers on active inference, and in all of them, the notation for matrices and vectors is used consistently, as in almost every linear algebra textbook. So I'm seriously beginning to suspect that every instance of a matrix or a vector not written in boldface is a typo, either in chapters or appendices, because otherwise I really cannot find any justification behind using two different types of notation. So I'm going to use this assumption as my prior for the rest of the book, unless someone has any belief updating observation she wants to share.
Yes, so just to summarize for the people that weren't there yesterday, we had a big debate about what does the bold typeface signify. And it wasn't so much a debate, but just like a mutual, trying to come to a mutual understanding. So it's this question here. Does bold lettering mean this is a matrix, but seemingly also many non-bold letters are a matrix? Or does bold lettering mean sufficient statistics of, as on these page examples? And it really was, we couldn't come to a single unified answer there, because there are many instances where it seems like it should be a matrix, but it's not bold. And there are many instances where sufficient statistics like are used, but it's also not bold. So yeah, we couldn't really conclude that. But I think, Ali, that's a good assumption there. So we also talked about this a little bit last time, but we didn't really get fully into this question. What is the use of categorical distributions in equation 4.5? The second line is supposed to explain the cat notation, but I have problems to understand the advantage of the notation. Could someone explain it in simple words? Does anyone want to try to explain that? I can pull up the equation.
Well, I think every regular matrix and vector is, by definition, an array of ordered elements. But in a categorical distribution, we don't necessarily assign any specific order to the elements. So the reason behind using the categorical distribution might be to just jettison any orderness in the elements and treat them as just an unordered set of the probabilities.
I wrote an answer to this one, if you want to pull that up. So you can just read that. So I hope this is helpful. It's basically, the way I see it is you have the math notation there, but when you need to actually implement that, you need to carry it out, then you need to turn that into operations you can perform. And so when you say that A is this categorical object, that means that you're turning it into an actual matrix with elements. And so the ordering is important, actually, because the ordering of the elements in the matrix says how that matrix is going to apply to the objects it applies to, which are the belief state S, and then your observation O. So basically, it says the way you carry out inferring what O will be, the probability of O given a belief state, is you do a matrix multiply. And because in this example, the states are not continuous, they're categorical, then you need a categorical matrix, elements in order to do map from the categories of belief states to the categories of observation states, and those are both distributions that gets transformed by the matrix.
Thanks, Eric. That was super helpful. Does anybody have any further question or comment on this one?
Sorry, Eric, but isn't the categorical notation special case of multinomial distribution, categorical distribution, special case of multinomial distribution? And I don't know, that was my
case.
Yeah, because that was my understanding, that the main difference between any categorical distribution and I mean, the lack of for instance, if we, of course, you're right that in any matrix, we necessarily have some ordered elements in order for us to be able to compute the math on those matrices. But on the other hand, for categorical distributions, at least that was my understanding, that we don't necessarily treat them as ordered elements, such as, I don't know, the ordered vectors or ordered matrices as the normal matrix. Because if that was the case, well, we could just designate this distribution as just a regular matrix, right? So I don't get what's the reason behind using the notation here, cat A or cat C here, instead of just using the name of the matrix itself.
Steven, can you mute? You're super loud over there. Sorry.
Yeah, I guess so. I mean, yeah, so the mathematical notation doesn't have an ordering. It just says distribution is related to another distribution through this this relation. And it's when you get to the mechanics of how do you do that, that's where you care that you have the matrix with the vector ordering. So yeah, I don't know what cat A actually means, other than it's just describing it. It's saying, I don't think it's like an operator. I think it's just saying what it is. Does that make sense?
Steven, if you're trying to talk, we can't hear you loud. I feel like Steven is trying to share an idea with us, but is unable to communicate effectively through the technological affordances he's been given at the time.
It's like the gain on your mic is way up or something. So it's picking up more background noise than you.
So just looking at this equation, let's try that again. So just looking at this equation, can you guys hear me okay? Yeah. Yeah, okay. So just looking at this equation, the second part, it's like it's like an ordered matrix, Aij, where the probability of the observations are equal to index I and the states equal to index J, something like that. I don't know. It looks like it is ordered.
Yeah, the matrix itself is ordered.
Yeah, and so the second line is actually by how the authors are defining this cat A. So cat A represents this ordered matrix Aij. Yeah, that's at least what it says in the textbook. So it says the likelihood expressing the probability of observations conditioned on time tau given states S conditioned on time tau is equal to the categorical distribution A. Okay.
If I may,
Sorry, Jakub.
Go ahead.
sorry, my internet is lagging a bit, so there might be a delay and I might break off. But I just want to comment that I think that the cat notation is really just to like reinforce the notion that it's in discrete time, but I think it's kind of redundant in this case because since we know that we are in discrete time, we could have just written a bold to signify that it's a matrix, and when it's a matrix, it's probably not going to be a continuous distribution anyway. So I think cat bold A and bold A is pretty much interchangeable.
So I think that some of the new math is using some of the affordances from category theory more, like some of the newer things, and I think like the forward direction that Carl and Thomas and some of the people that really helped derive and advance some of this math. I think that they're going to be leveraging category theory methods like the renormalization group and the pullback attractor more in the future, and so that might be also like part of the reason that they are moving toward this categorical notation. So just a little maybe foreshadowing there too.
And may I just make one additional note about this categorical distribution? Well, the thing that confused me about this concept of categorical distribution is Wikipedia's definition of it, because here it says there is no innate underlying ordering of these outcomes, but numerical labels are often attached for convenience in describing the distribution. So that was my confusion and mistake.
I don't think it would be the first time that we've seen traditional mathematical notation slightly and somewhat abused in active inference. Probably also won't be the last, but definitely I think it's a point that we can put forward to the authors for additional clarification. If there's no further, anybody has anything else to say about the categorical distributions here? If not, we can move on to maybe the next question. So this next question reads, in message passing, is there a decay of information as the distance between the variable x and individual Markov blanket constituents increases? Is implementation of information decay in message passing an option for model implementation? I think that this is a super interesting question, and it's something that I've thought about before a lot. But I think, yeah, let me open it up to anyone and see if they want to address it before we can get into some of the discourse.
Well, doesn't that all depend upon the chain of loss between one stage of the message passing and another? And if you have no loss, then you don't have any decay. But the more stages you have where you get a little bit of diffusion or loss, then you're going to have decay. Just a function of the parameters.
Well, so are messages passed within the same Markov blanket or between things that are partitioned with their own Markov blanket? That's another question.
I also agree with Eric, as I mentioned yesterday. I also believe that this information loss is not accounted for, at least inherently, in active inference formalism, because it depends on the specific situations that those information propagate. Because otherwise, we couldn't have any general or all-encompassing formalism for accounting for these information loss.
So we see in this box, they talk about Markov blankets and the message passing. So here it's variational message passing. This involves messages from all constituents of the Markov blanket of X, including the parents via the conditional probability of X given its parents and the children. The latter depends on the conditional probability of the children of X given all of their parents, which include X. Note the expectation includes the children and parents of the children. As parents of the children X, we divide by Q of X to ensure the expectation includes the blanket only. So I think the messages are like all of the things inside of the blanket send a message to something else in another blanket. At least that's how I interpret this way of active inference. And so it would make sense that like from within the blanket, does everyone have the same, is there like a high degree of mutual information shared in the Markov blanket? I think like conditional dependence is what qualifies as like conditional independence is what establishes the Markov blanket. So within constituents under the blanket, do they all have all of the same information all of the time? That's something that's kind of confusing to me.
One thing I'd point out about figure 4.3. So in the previous chapters, we have this picture of there being the world and your model of the world, and those being and your model of the world is a Markov blanket itself, and it interfaces with the world through the observation variables and the action variables. This picture doesn't have that breakdown, so it's got state there, but it doesn't say what is that state all internal state, is it external state, or a mixture of them. And it's apparently is mixture because you've got policy that can affect state, which means that you're going to have action is going to be part of the state transition, as well as and then you have the observations coming out the bottom. But I think if we're going to talk about Markov blankets, then I would like to see this picture be exploded into the internal, the state of the machine versus the state of the external world and how those interact with one another, because that's what the Markov blanket does, is it compartmentalizes the information.
Well, and so that is the POMDP model in figure 4.3. And this really, figure 4.4, is like makes me scratch my head quite a bit. This is the image that is going to like represent message passing in a Bayesian framework. And so the caption says, on the right, dependencies between different variables in the belief updating scheme outlined in the main text. Intuitively, current beliefs about states under each policy at each time are compared with those that would be predicted given beliefs about states at other times. This is 1. And current outcomes to calculate prediction errors. These errors then drive updating in beliefs. This is 2. Given beliefs about states under each policy, we can then calculate the gradients of the expected free energy. This is 3. These are combined with the outcomes predicted under each policy omitted from the figure to compute beliefs about policies. This is 4. And then using a Bayesian model average, we can then compute posterior beliefs about states averaged over policies. This is 5. Yeah. So and this kind of leads us into the next question, but like I am not able to really interpret this figure 4.4 in any better way. So if anybody has like a plain English description of how this works, I would love to hear it. We can also we can talk a little bit about a question that was raised about this figure and also about this like squiggle sigma, because there's a great like I don't know. I mean, we kind of had a hard time figuring out the equation and the squiggle sigma and what that actually stands for. So we could move to that discussion because I think it's maybe related to this message passing discussion. But let's read the discourse here first. On the message passing question. So in the discourse, what is the mechanism for signal decay? So this is information decay, implementation of information decay. Is the message a thing behaving as an active inference agent itself, or a special piece of information not behaving as an active inference system itself? Is there a blanket impedance mismatch? I think Brock contributed this. I'm not sure if he's here today. And then message passing as described through active inference usually is a hierarchy, not a lateral transfer like within constituents in the blanket. So the key thing here is how you define the Markov blanket. Either there's a partition between particles, cells, or whatever, or there's no partition in blanket and everything under the blanket is conditionally dependent. Does conditional dependence preclude message passing? Are message passed within nodes in the same blanket? I have not seen this and would love if someone pointed me to some references. So that was me. I wrote the last part because I haven't seen message passing under the same Markov blanket. It's always been like from one Markov blanket partitioned object to a different Markov blanket partitioned object. But that moves us into, if anybody has any comments, feel free.
Well, I would say message passing is used to do the inference, so it's within a Markov blanket. I mean, that's pretty common, I think, in the message the way message passing is used.
So here, as it's shown in figure 4.4, like although this is totally like beyond me to describe, here this is a temporal message passing. So it's like from one time point to another time point. And then on the left, it depicts the hierarchical, like a hierarchical expansion, collapsing over time steps, but that a higher level network might predict the states and policies at the lower level and use these to draw inferences about the context in which these occur. So the way that I've always seen the message passing used is from one time point to another, or from one layer of a hierarchy to the next layer of a hierarchy. And I've not seen it passed within like constituents under the same Markov blanket. So Eric, if you have references that depicts like some kind of message passing in active inference that's not through time steps or through hierarchical levels, I would love to see that because I have not seen it.
Well, I would just go back to box 4.1, where they talk about the variational message passing and how you get information. And I would say within a blanket, you've got various nodes, and they have this hierarchical parent-child relations. And in order to do inference about, hey, what's our belief in one of these parents, you got to kind of go up and down and say, well, what are the children of that, and what do the other parents think? So that's all within a single markup blanket, the parents and children, the hierarchical relation, and the message passing happens to circulate that information within the blanket. That's how I read.
And I also put a link here to a paper by Champion et al., in which they have actually explicitly defined the active inference, or better say, reformulated the active inference formalism according to a variation of message passing. And if you just give me a second, I can find exactly the place where they have stated this in plain English. Just you can continue with the other questions if you like, but I need a moment to check this paper.
Sure. Yeah, I'll check it out also. And yeah, thank you for that. So like when I'm reading this variational message passing, this involves messages from all constituents of the Markov blanket of X. So the message is coming from all the constituents in the blanket, but it doesn't say where the message is going. So it does make sense, like that. I guess that it's an interchangeable, like, or within would be a better word than from. Like within all constituents of the Markov blanket. Because I was reading it as like the message is coming from everything under that blanket, which I guess is an incorrect interpretation. So thank you, Eric, for pointing that out, because I was like, what? So this is a really hard question that I looked to try to answer. Actually, a bunch of us looked yesterday a lot. So it says in equation 4.10, the sigma variable, squiggle sigma, we'll call it whatever. I'm not sure how to say it, is used to describe the difference between the natural log of observations conditioned on policy and preferences. What is the function of this variable? It also comes up in figure 4.4, the message passing figure we were just looking at, and it would be great to have a verbal description of this figure. What other papers or equations use this squiggle sigma? And we looked at length, like through the entire textbook, through the other chapters it refers to, like we'll unpack this later in chapter 7. We looked through chapter 7, we looked through the appendices. We saw a variable that almost looks like that, but I think it's a gamma. It looks like a little bit more fancy than this squiggle sigma, and could not find that at all. So we went to unpack equation 410. And so here is the equation itself. I'm not sure how to put this up next to the, actually, maybe I'll put it up here. 419. So, and this equation 4.10 is a rewriting of equation 4.7 in linear algebraic form. So we tried to kind of unpack this a little bit. So the first line states the prior probability for each policy, this is that pi sub 0, is equal to the softmax function sigma times the negative expected free energy g. And so that's this first line. The next line is the expected free energy conditioned on policy, g sub pi, is equal to the entropy or negative expected log probability, h, times the states conditioned on policy and time, which is s sub pi times tau, or both of those sub pi and tau, plus the observations conditioned on policy and time, this o sub pi times tau, times the beliefs conditioned on policy and time, which is the squiggle sigma, maybe, sub pi times tau. So we were kind of unsure if beliefs is correct here. We kind of pulled that out of the legend for figure 4.4. But if anybody knows, and just to maybe unpack that a little bit more, the beliefs conditioned on policy and time, the squiggle sigma sub pi times tau, is equal to the difference between the observations conditioned on policy and time, O sub pi times tau, and preferences conditioned on time, C sub pi or sub tau. So we were unsure if belief is correct here also. And so if anybody knows if beliefs is the difference between observations and preferences, that would be great to have some kind of feedback or input here, because we couldn't really reach a conclusion.
Well, I guess one tiny step toward figuring this out, I would say, is that that funny squiggle thing there has to do with the C. We've got this probability of observations given C, and C is this mysterious object that expresses preferences, which has also been under-explained. And that's, so if you look at the two terms of the expected free energy, G, as a function of policy in 4.7, and then look at how it looks like in 4.10, that sigma thing there is expressed as we've got the dot, which I guess is a multiplier by observation. So that's the same as, that's like saying your probability of observation given C. So that's, I guess, a matrix multiplier version of the this log probability of sequence of observations given your preference prior C.
Yeah, so they do unpack it a little bit more in equation 4.7, or it seems to be like maybe we could extrapolate from 4.7 if this is beliefs, because it is this natural log of observations minus the natural log of preferences. But up in the top, that just the free energy is the entropy, or maybe the dot product of the entropy times the states plus the observations times, or the dot product of the observations and maybe beliefs here. So I've not seen, like, I can't recall a mathematical representation of belief ever using this squiggle sigma before. And I looked through the recent Ryan Smith paper, and I looked even at like the message passing paper by Friston, and I was not able to really get any additional like references to this squiggle sigma at all.
So why do you say belief as opposed to preferences?
Well, so it says here that the squiggle sigma is equal to the difference between the natural log of the observations conditioned on policy and time and the natural log of the preferences at a certain time. So the sigma is defined by the natural log of the preferences, but it's more than just the preferences. Does that make sense, Eric?
Yeah, but that's not the same as belief, right? That's observations versus preferences.
Right. So
Well,
the difference,
like an error rate from expected deviation, or how much risk is being taken relative to the policy that's applied. So because I mean, it's the dot product is between the observation and that squiggle sigma, right? So which is in turn like, okay, this is what I've observed. This is what I expected. So it's like a divergence between the two. So how much more risk am I taking, and how far is this pushing me away from my from minimizing free energy? So maybe it's something like that.
Whereas belief is wrapped up in the S, because that's your model, of the world.
So risk is maybe how the squiggle sigma is defined. But then if you look into this figure 4.4, like that's why we used belief. So here, I'll pull it up right now. So I'm not sure how easy this is to see, but before we get to number 1 here, we have like at the second on the right hand side, the second to lowest level is states conditioned on policy and time. I think I'm going to read it off this bigger screen. Oh yeah, states conditioned on policy and time at different time steps. So like the current time is in the middle, the forward time step is on the right, and the backward time step is on the left. And so that's what we start with. So intuitively, current beliefs about states under each policy at each time are compared with those that would be predicted given beliefs about states at other times. So maybe beliefs is this S. Well, and that's kind of what Eric was saying. And we know because it's defined earlier, this epsilon here is a prediction error, right? So what we come to after step 1, it says, and current outcomes to calculate prediction errors. That's what we arrive at after number 1. The errors then drive updating in the beliefs. That's number 2. So here we go from the current state at the present time to a prediction error that drives the belief updating at the forward time step after number 2. And then it says, given beliefs about states under each policy, we can then calculate the gradients of expected free energy. 3. So what gives us this gradient of expected free energy? Is it this S sub tau plus 1, or is that a tau? I think that's a tau. Let's see. Yeah. So is it a future state not conditioned on policy, or here we get to this squiggle sigma? So it's a squiggle sigma conditioned on policy and time plus 1. So it looks like a belief update there, which is why belief made sense. So is that a risk update? Is that a possible interpretation there in this message passing figure?
Well, they say it's a gradient, which means it's saying how much do we have to change our policy? I think in order to get our objectives.
Yeah, gradient makes sense to me as well. Because it's how much information you've gained, right? So if you actually look at the change in the state with respect to, so I apply some, let's say, force, or like, let's just take a simple example, right? Like if you have an actuator that just applies force, and all it does is it moves forward and has to follow a trajectory. So the error is, so at each time step, if it's a deterministic system, you expect it to follow a straight line, and it's deviating away, so that's epsilon. So you have to update, okay, this is how far I am from the state that I'm supposed to be, so I need to apply slightly less force, or maybe a force in a different direction. And that seems, so it's also how much I have to overcorrect in the future depending on what I've done currently, right? It's not just so if I've applied some force right now, I might deviate in the opposite direction, and I have to come back. So I have to figure out how much force to apply. So that's why I said risk, or gradient. You would have to take the change with respect to the state change with respect to the error. So that would be one interpretation of it, right? So it's a gradient of the state change with respect to what you have done.
So I also heard the term information gain in there.
Yeah,
which
yeah.
is
I mean, I'm just generally saying. So in neural networks, for example, we would have like some sort of loss function, and we would calculate the weight change with respect to the change of the loss function, right? So like I have a weight vector, and then this particular example is giving me a certain amount of gradient, and I need to minimize this gradient, so I need to change the weights in turn. So the gradient actually interfaces between this loss function and all these weights. So effectively, the gradient passes on information as to how much the weight has to change in order to minimize that loss function. That's why I said information gain.
And also, as a side note, I think I found this sigma in Ryan Smith's paper too. And it is defined as the expected prediction error.
so the expected prediction error versus the actual prediction error, like, and they distinguish it from epsilon in the Ryan Smith paper, because I did look at that, but I didn't find it in there.
Yeah, it's in equation 27 under the section outcome prediction errors.
It may be that the expected means it's an expectation over the Q distribution, which is your distribution over belief states.
Yeah, that's great, Ali. Like Ali and I and some others worked on this yesterday a lot, and it's great that it kept you up late at night. Clearly, Ali, so you went digging around for for some more information. That's awesome. Yeah, great. Okay, perfect. Well, that resolves that very well. And then let's get into maybe the next question. All right. So in equation 4.16, the x has a dot over it changed through time, but not the y data. So there's some discourse on this. Or maybe we should go to the next question, actually, because it's maybe more related. So figure 4.6 uses an epsilon for prediction error as described in equation 4.21. Is this predictive processing framing a part of the active inference model, or is this presented for contrast to illustrate the similarities and differences between active inference and predictive processing? So this is equation 4.1, and this is the epsilon, but I think we see it way before equation 4.21. Like it's even there in equation 4.4. It says, this predictive coding schema is part of the active inference model, illustrating the hierarchical structure of predictions and beliefs. The authors say, one way to think about this is as if we had equipped a predictive coding scheme with classical reflex arcs at the lowest level of the hierarchy, and they give this reference. In this setting, active inference is just predictive coding plus reflex arcs. Does anybody know what a reflex arc is? Because I'm a little bit lost with respect to that. Or have any comments on this prediction error?
Yeah, reflex arc is well, basically the stimuli that doesn't go through the sensory cortex.
I thought it was like a mathematical construct.
Maybe you think of it as a control system. No thinking. It's like, you bang your knee, your foot goes up.
Yeah, that makes sense. And it says we minimize free energy through action. And the only part of the free energy that depends on action is the lowest level of prediction error in this hierarchical schema. Action fulfills descending predictions by minimizing the error between the predicted and observed sensory data. Any additional comments here about predictive coding and active inference? Or we can look at this equation 4.16. The x has the dot over it, changed through time, but not the y data. Why is this? And here the discourse says the top equation depends on f of x and v, which is a deterministic function describing how a hidden state changes over time. The bottom equation depends on g of x and v, which describes how data are generated from a single hidden state. The tilde indicates change through time. The dot indicates the first order derivative. Any comments here on this equation or question? So maybe we can ask one more question or maybe a couple more. So here it says on page 63, it says specifically the Bayesian brain helps us frame the problems that an agent engaging in active inference must solve. Broadly, these are the problem of inferring states of the world, perception, and inferring a course of action, planning. Other than perception and action planning, are there other tasks or challenges that the brain or organisms engage in? How would we know? There's no discourse here, but let's open it up and see what you guys think.
People wonder, hey, what's on that star out there? That's neither, I don't know, is that inferring state of the world? I guess. Not planning.
And it could just be a hallucination of the generative model. You're not really measuring anything. You're just measuring yourself over and over again. That could be one thing.
Okay, so here there's another question. For each of the graphical models in figure 4.2, what is an intuitive example for each structure?
One would be disease diagnosis, right? So you have symptom that is causative of or predictive of some condition.
I think that was the example that they gave in the text, right? Or did we talk about this last week, maybe?
Yeah, I actually don't get the question because for each of them we have an example, at least an example in the text. So
Yeah, that's true. And I think we're going to maybe see more examples as we go through the book.
But just in case, if anyone wants to see some more examples, actually that paper, I put the link in the chat, Realizing Active Inference in Variational Message Passing, contains some more examples for each of these diagrams.
This is a fun last question, maybe. It says, this reiterates that active inference uses two constructs, variational free energy and expected free energy, which are mathematically related but play distinct and complementary roles. In your own words, what are the definitions of variational free energy and expected free energy, and what role do they play individually or together in active inference?
My view of expected free energy was given a certain action that might be taken, it might produce this or reduce the free energy or some, or it talks about some future reduction in free energy or something like that. Variational free energy is more objective. I don't know how to put it. It's like okay, actual kinetic energy versus perceived kinetic energy kind of thing. So if you're rolling down a hill, yeah, like a ball rolling down a hill, we can actually measure the kinetic energy at the bottom of the hill, right? If you put the ball at the top. Expected free energy would be like using a model to calculate that and then finding out it actually corresponds if you have the model. At least that's my view of it.
So I don't know, I'm probably like, I think about this in a lot of different ways, but I think about like variational free energy. I mean, this is one way to think about it, is like maximizing like the trade-off between epistemic value and pragmatic value, like right now, and expected for free energy is like maximizing that difference at some point in the future. So you can like plan ahead. Like it might be cold out, so I'm going to take a jacket. Or like it's cold right now, I'm going to put my jacket on. Those are kind of like, that's how I think about the difference between those two. So it's 10. Thanks everyone for coming. I hope I didn't, muddle this up too much, trying to be substitute teacher for Daniel. It's 10. So we're going to have tools right now in this room, but if anybody wants to continue discussing these ideas and gather, you're welcome to migrate up to one of the different spaces. Yeah. And I think we'll stop the recording now, Alex, if you haven't already.